All right, this is the video solution for problem number 3. So essentially, here's your origin. There's a tree that's 17 meters away, and 8 meters above the floor, there's a knot in the tree. You're shooting a paintball directly at the knot in the tree, and its initial velocity is 50 meters per second. So it wants to know, when the paintball strikes the tree, how far below the knot is it gonna fall? So there's a few things we need to figure out here in order to do that. And the first step, using our projectile motion equations, is we have to figure out the time it takes for the paintball to hit the tree. So we can figure this out. Essentially, we have a triangle here that's the adjacent length of the angle theta is going to be 17 meters and the opposite is 8. So we can actually figure out this angle here by doing the inverse tangent of the opposite 8 over 17. So if we do tangent -1 of 8 over 17, Mac, please, 1 minute. That's gonna equal our angle. So let's see, let's find out what that is. Inverse tangent of 8 divided by 17, that gives us an angle of 25 degrees. So we know theta is 25 degrees. Now that we know what theta is, we can figure out what the initial velocity in the x direction is. So we know the initial velocity was 50 meters per second. So, and then this is now 25 degrees. So if we do, I'm trying to think, I gotta remember this cosine. So, so we're gonna do cosine of 25 times 50 is gonna equal to our velocity x in the initial, our velocity in the initial direction of x. So let me plug this in and see what we get. Cosine of 25 times 50. So our initial velocity in the x direction is 45.3. I know that the horizontal and the projectile velocity is consistent, so that's going to be our final as well. So that's equal to 45.3 meters per second. Now that we have that information, we need to figure out how much time it takes. So if we use the kinematic equation, and I don't memorize, but x final equals x initial plus velocity in the x direction initial times delta t. So we know our final is 17, our initial is 0, and our initial velocity we have. So we can solve for delta t. So setting that up, we'll have 17 is equal to, let's see, can you see this here? 17 x final is equal to x initial plus 45.3 meters per second times delta t. So basically, if we do 17 divided by 45.3 meters per second, that's meters. We're gonna end up getting our time here in seconds. Let me do the math of that. So 17, 45.3. So it's gonna take, time is about 0.31 seconds to hit the tree. Think about that logically. Does that make sense? 0.3 seconds to go 17 meters. 17 meters. Hold on. It's 56 feet. I guess that's realistic, yeah. Okay, yeah, that's right. So now we know delta t is 0.31 seconds. Okay. So now that we have delta t, we can actually go to the kinematic equations in the vertical direction, or not the kinematic, the projectile motions in the vertical direction. So y final is equal to y initial plus velocity in the y initial direction times delta t minus 1/2 g delta t squared. And we have those as well. Wait a second. I think I've done my math wrong from what I'm seeing here. Let me just run through it again. Tangent to the -1 of 8. So then the cosine of the second answer times that by 50 gives us 45.24. 17, 3.7. So I rounded throughout that, and I'm actually not going to do that. So my time, if I just ran through those equations again, my delta t is actually 0.3756765 seconds, which I guess it makes sense not to round. I don't know if that makes a big deal or not, but we're going to keep it. So now that we have that information, we can go forward, do the vertical direction. So basically we can figure out where this is going to fall in the y direction. So to figure out the y initial, velocity of y initial. Huh. Yeah. Yeah, let's roll with it. Okay, so we're going to use the y final equals y initial plus vy initial delta t minus 1/2 g times delta t squared. The only thing we don't have is the velocity in the y direction initially, but we can figure that out because we have the angle and the initial velocity. So we're going to go ahead and do sine of 25 times it by 50 gives us an initial vy initial is equal to 21.1309 meters per second. So using that, now we can figure out the rest of this. So y final equals y initial. So we want to know the y final, but the trick about this is that I'm going to disregard the 8 meters up that the knot is on the tree, and I'm just going to go ahead and say that my y final is 0, and then that will give me the y, or my y initial is 0, and then my y final is going to be wherever it is up on the tree, and then I have to find the difference of that to figure out how much below that it's going to be for of the 8 meter knot, which is what the question asks for. So y final, which I don't know, is equal to y initial, which is 0. What's the rest of this equation? Plus velocity initial, which is my 21.1309, times the time, which is 0.375765, minus 1/2 g, which is 9.8, times the time squared, 0.375765 squared. So running through, this is the equation here, which is the y final that we're solving for. We just talked about, so I'm going to go ahead and figure this all out. 375,765 squared, times that by 9.8, times that by 0.5. So we get 0.69 for this portion. We're 21.1309 times that by 0.375765 is equal to that. We're going to subtract that from this. So y final is actually going to be equal to 7.24. Well, no, I'm not going to round. 7. Sorry, it's hard to hold both of these. 7.24837 meters. And that's going to be up the tree. So the question initially asked for how far below the 8 meter knot is the paintball going to hit. So this is how far up the tree it is, because I used my initial y value as 0 instead of correlating it with the 8 meters. So I'm going to do 8, subtract that answer, and that'll tell me that the paintball is going to fall about 0.75 meters above or below that notch, 0.75 meters below the notch, which, if we think about that, meters, so divide that by 0.3048, that's like 2.5 feet below the notch, which makes sense. That's not that big of a difference. So That's all in all. So to recap it, we basically had to figure out theta, which we did using the inverse tangent function. After that, we used the vertical projectile motion equation to figure out what, that's not there, to figure out the time that it took for the equation to happen. And then we went over to our vertical y final equals y initial equation to figure out how far up this ends at the final position. And then we took 8 meters and subtracted that to figure out that it fell about 0.75 meters below the knot.